Hopefully this will be faster and more condensed than the lesson version. Okay, the first thing we need to actually prove is there's a relationship of dy dx is equal to 1 over dx dy. This is allowable because what we can actually realise is that if we treat it purely as the gradient at a point, the gradient at the point is equal to the y over the x, which by fractions means that we can actually turn this into a reciprocal. So we can actually say this fraction is actually equal to 1 divided by delta x, delta y. And if we take the limit as delta x goes to 0, we are saying that the gradient here is actually, oh sorry, let's not do the limit yet, is actually dx over dy, delta x over delta y. Then dy dx is the limit as delta x goes to 0. We get dy dx, and in the same way we get the same terms, dx dy. So that's the first piece we need to be able to do work with logs. The first thing we're going to look at is, by definition, the gradient and integral of e to the x is e to the x. And the reason that comes about is, if we look at any function in terms of a to the x and its gradient, if a is small or relatively small, what we can get is we can get the gradient, which does that, and when we find the function that does that, its gradient we find does one of two things. It either mirrors it but below and slightly shallower, and that's if a is less than some value, or if a is greater than a key value, it goes above, but it still mirrors the shape. It looks like it's something, some product of that shape. And that's what we were looking at in this part. When we've got less than a value, green is the function, the derivative is red. As we get close to some key value, they swap over, and the red becomes steeper than the green. The key value is around 2.7, but they suddenly seem to be the same. And that is where we get our definition from. So when the differential, so by definition, there is a value of a that is equal to some special number where the differential of e to the x is actually the same as e to the x. It also has the corresponding follow-up that if you actually do the area from 0, the integral of e to the x with respect to x is also e to the x. So let's go into a general form. dA to the x dx. And we need to find out some expression for it. Well, we know the differential of e to the x is going to give me some value. So what I'm going to do is what appears to be a fairly silly piece of algebra. We're going to take the logs and then do the exponents. So if I take the y equals a to the x, and it's changed. If I take the log of both sides, and I'm doing the natural log because we know about e so far, we don't know much about any other logs. This is where we start getting formulae for logs from. If we do the natural log of both sides, we get a way of rewriting this right hand side. Log a to the x can also be written as x log a. Now if I come back to working out what y is, y, raise it to the power of b, gets rid of the log, and raise the right hand side to the power of b, and that is still the same as a to the x. We need to remember that's still the same thing. So now what I can do is, let's try differentiating what's happening here, and we're going to differentiate using the chain rule. So now we're going to do dy dx of a to the x, which we now rewrite as the differential of e to the x log a, and I say u equals log a, no sorry, a log x log a, you get rid of the x, don't I? So u equals x log a, and du dx is just log of a. So when I do this differential, using the chain rule, we're going to get, we're now trying to differentiate du with this function in, e to the u, and then times by du with respect to x. From above, de differentiating exponent gives me e to the u, and the du dx is log a. Put my value back in, and we get ln a log a e to the x log a, and we suddenly realise that x log a all the way back up here is also ax. So we now get log a times a to the x. So we've got a way of differentiating a general exponent by taking the natural log, must be natural. Let's just highlight the key notes coming through. So our first one is that rule. Second one is all three of these. Excuse me, those two. The third one is this one. Now we're going to find the differential of a, differential of log. So I need to work out how this one works. Okay, ready for the next bit. Just sorting my mind out on what we were doing. So we're now going to do what happens when y is log of x. Well, we can say one thing that we need, which is dy dx. We can find, if I know how to do the differential of dx dy. Well, the differential of dx dy we can now do is, if I rewrite this in terms of x is e to the y. Dx dy is equal to e to the y, which is also equal to x. So by substituting this back into here, we now have dy y equals log x. Substituting in here, dy dx is equal to 1 over x. And that gives us our general form. So if I write it a little bit more formally as a box. So using these two parts, the differential of log of x is equal to 1 over the dx dy. Well, dx dy we found out was x. So it's 1 over x. So we can get our values out. from there. So that's our log proofs that we need for differentiation.